It won't take you too long being in the technology world to realize that there's this concept out there called the OSI model that people will keep referencing again and again and again. And if I look at my history, I started off in the Microsoft world and was there for a couple of years and moved into Novell and did that for a couple of years before I got into Cisco. And all along there was this mythical concept called the OSI model. And anytime I'd be in other network administrators, they'd be saying, "Oh yeah, that's definitely a layer 4 function." Yeah, layer 4 function. I would kind of go along with it, and not really know what I was talking about. Kind of, at the same time, I was in this technology. Taco Bell came out with their 7-layer burrito, and I'm thinking, what is the 4th layer of a burrito? I had no idea what the 4th layer was all about. Now, that's because in the Microsoft and Novell world, you learn what the OSI model is, as in it's a model, it has layers, and each of these layers do things. But you don't really do anything with it because you don't really deal too much with networking in the Microsoft and Novell world as you do in Cisco. And it took me getting into Cisco to realize how foundational the OSI model is all about. So what I'd like to do in this video is to walk you through what the OSI model is all about conceptually, then apply it to real life. So you can see that this is not just a model that we look at and say, oh, well, there it is. Let's put it on a wall with a frame around it. This is something that we can apply to our daily jobs in the network world. So if you haven't seen it before, let me be the first to welcome you to the mythical OSI model. There it is, all 7 layers of its glory. Now, your number one task when looking at the OSI model is to memorize it. Unfortunately, that's just going to be one of the kind of green bean casseroles that you have to swallow. Where did that come from? These are the layers. We have physical going from bottom up, data link, network, transport, session, presentation, application. My favorite acronym, that would be the word, to remember that would be please do not throw sausage pizza away. That is from the bottom up. Or some people like to say all people seem to need data processing, moving from the top down. That'll help you get the first letter of each one of those and remember the order that they're in. So while you're busy memorizing that, let me talk about the function of the OSI model. The OSI model is a system that helps you break down network functions. And let me compare that to something that might be more familiar to things that we work on day to day, like houses. When I go to a construction site and I'm watching houses be built, I know that somebody didn't just walk in there and say, let's just build a house, right? Let's grab some boards and stick them over there. You need nails to build a house, so let's throw some nails over there. Oh, I know we'll need some concrete somewhere in here. They don't do that. They kind of think of building houses as phases of projects. And if you drive by big office buildings, they'll always say, yes, we're in phase 1 or phase 2 of construction. It's kind of like the major steps that they're going through to build that house. So phase 1, and again, you'll have to forgive me here. I am not a construction guy, so if I get my phases all mixed up, that's okay. Concept still applies. Phase 1, we've got to lay the foundation, right? We've got to pour some concrete, level out the dirt, get a flat surface there, because if you build the house on sifting sand, if you will, it's not going to stand very long. That's biblical. You need to make sure that you have a solid foundation to pour this concrete, level it out, and make sure that this thing is going to stand. So phase 1, lay the concrete. You have a specific crew to do that. You mix up some concrete mix, and there you go. Phase 2, and this is where my construction experience breaks down, right? Let's run piping. No. Yes. No, that should have come before the concrete. It all breaks down. But you get the concept, right? There's these phases that we focus on, and we have specialized people, specialized equipment, specialized goals that we're meeting for each one of these phases. In the same way, the OSI model helps us break down network functions. For example, if someone walked up to you as a network administrator and said, the network's broken, your next question would be, What on the network's broken? Is it that you can't surf the internet? Are you not able to access the server? Or your email down? What's going on? So you'd really have to focus in to figure out what they're trying to describe, because otherwise, I mean, a network's a big place where things could go wrong. So this helps you break it down the network function. Number two is it creates standards for equipment manufacturing. There are vendors that can make specific devices for the specific layers. Give you a quick example. We haven't described the layers yet, but we will in just a moment. Down here, we've got the physical layer. The physical layer describes physical connectivity, things that cable, things that plug in. When you think of physical layers, literally think of physical things that you can hold in your hands, like network cards, like cable, like WAN connection interfaces, wide area network interfaces that let you connect across the world. All of these have different physical standards, and you might have a manufacturer that focuses on nothing but this layer. Just like for the house, you might have nothing but a concrete layer that can, have specific people that just lay concrete. When you move up to the data link layer, that's where we can start moving into functions that describe that specifically. And without getting too far ahead of myself, things like the MAC address exists here. Things like network switches work on at this layer. So you can have manufacturers that just focus on building network switches, and all they do is focus on the data link layer. Likewise, that allows vendors to focus in the specialized areas of the network. This is what I'm getting into. Allows them to build what their company is designed to build for. And the beauty of all this is there is a standard that will be followed that allows all of these to interconnect. For example, in the house world, if the concrete layer didn't lay a solid foundation and really follow a standard and use the standard kind of concrete mix, then the next person that's going to build on top of that foundation of the house, the concrete starts cracking and falling apart and liquefying below their feet. They're going to be like, the concrete layer didn't follow the standard. In the same way, we have all of these standards. Like there's certain physical standards you got to adhere to in order for the data link layer to connect into that. And the data link layer has to have certain standards in order for the network layer to tie into that. It guarantees that all these manufacturers are building stuff that work the same way. So that way I could buy, a network switch down here from, we'll say, Cisco, because they sell network switches. And then maybe down at the physical layer, I buy some cabling from. I just whipped around to look behind me. I'm like, what's a cable vendor? Quick, find some cable. Look at the tag on it. I don't know. From Cables Unlimited. That's a place I've bought from on the internet. So Cables Unlimited manufactures physical standards that will allow you to interface with that data link layer. So let's start walking through the 7 layers of the OSI model, layer by layer. You might want to keep this video in mind for future reference. For example, if later on in the series, maybe we're talking about layer 3 of the OSI model, and you go, well, what was layer 3 again? You can always come back here and reference that. So we'll start where just about all the applications begin, at the application layer. Now, the application layer is the most familiar layer because this is usually what you see, the application itself. It provides an interface that allows applications to communicate across the network. So if you're using some kind of application that is network aware and has the ability to send data across the network, like a web browser or email, or maybe it's even World of Warcraft, an online game that communicates on the network, it sits up here at the application layer and begins its communication from this point. Now, as soon as it starts sending data, it will pass through the presentation layer. This layer generifies the data. You know how Wendy's has super size and giant size and things like that? This is what I call generifying. The data becomes formatted in a generic format that is understandable by whatever server you're communicating to. For example, maybe you're surfing the web and you go to usatoday.com to read the paper. Well, that web page is formatted in HTML format. That's a generic format that just about any web browser and every web server understands. On that web page, you might have pictures that are in JPEG format. It's a format that every web server and every web client understands. On that same page, you might have an advertisement that's playing some music in MP3 format. Again, a format that everybody understands. That's one of the functions of the presentation layer, is to make the data generic and compliant to standards so that the applications, when they're talking to each other, will understand it. Now, you also see that we have encryption services, namely generic encryption services at the presentation layer. Now, I know that might sound bad. Like when you think of generic encryption services, it sounds like it's not secure. But honestly, the entire internet uses generic encryption services. For example, when you go check your online bank account balance, you would expect that that would be secured and encrypted, and it is in a generic way, but the generic way is very good, that uses a set of keys that both the server and client possess that encrypt the data back and forth. It's generic encryption in a sense that the client and the web server will be able to do it together, but it is very secure. So data gets generified and passes down to the session layer. Now, the session layer is what starts and ends your session. Like when I first access a web server, it says, hey, I'm ready to begin a session. Let me communicate with you. And it keeps all the sessions separate. For example, on your computer at home, you might have 5 different applications open at the same time talking across the network. You have to have some kind of system that allows, the right data to go to the right program, and that's the function of the session layer. Now, as we move down to the transport layer, I'm going to draw a line right here. And I fell off the edge of my pad. There. That is the line. I would say, if I were to categorize them, that in the Cisco world, all of this stuff right here is the least important. It is the least important because all of that stuff happens before the data ever leaves your computer. Meaning that those top 3 layers, check, 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 is all handled by Windows or Linux or whatever operating system you're running. And really, when you're working in the Cisco world, you don't usually care about that. I mean, the Internet Explorer sends some information. It's been generified, so a web server will understand it. But the Cisco router and switch doesn't care because it doesn't look at it. Honestly, most Cisco devices never look past the transport layer. They just stop right there and say, I only care about stuff that's below that layer. Meaning, compare it back to the construction, I only care that the foundation is secure. I only care that the correct nails are used. So while it is important, of course, to understand what these are, as I draw a big X through it, those I would say are the least important layers. Let's look at what I would consider the most important. The bottom 4 layers, starting with the transport layer, which I would award the certificate of most important layer of all to the transport layer. The transport layer describes how the data is sent. Now, when you get into it, most of the time you'll have one big choice that you choose at the transport layer. You will either have the ability to send it reliably or unreliably. I'll just put un-r. Now you might think, well, explain that. What's the difference between those two? Because I'm thinking when I hear that I'd always want to send stuff reliably, meaning I make sure it gets there. And most applications do. For example, if you choose a reliable transport, or the application chooses it, because we don't choose anything, we open a web browser, it's going to choose a reliable transport. When it sends a packet to the server, it's going to expect that the server sends another packet back called an acknowledgement, meaning I got it. So when I send a message to the server and say, hey, I would like this web page, the server sends back a packet saying, I got it, and then it'll send a few more packets back to me saying, okay, here's the web page you asked for. So in the transport layer, we get to choose reliable to say every single thing that I send is acknowledged, so I know that it got there. Now, the reason that's beneficial is if maybe I'm sending a bunch of stuff, maybe I'm transferring a huge file across the network, and it's just sending a bunch of little packets to make that file up, and one of them, gets dropped along the way. Maybe it, hits a bad cable, or just gets scrambled and gets dropped. Well, since the computer didn't receive an acknowledgement back for that packet, it's going to back up and say, whoa, well, let me send that again. And it'll send it. And that's why every single time we send and receive files across the network, they all come through okay. And we double click it and it runs just fine. It's because we have a reliable transport. So with that definition, you might think, well, then why on earth would you ever choose to send something unreliably? Well, unreliable transport is typically used for something known as real-time applications. For example, one of the hot new things is voice over IP, meaning I have phones that run over the network. And as I speak into the phone, it's sending my voice in packets over the network. Or another hot thing is video over IP, where you can actually watch television online or stream a movie through the network and watch it on your TV. Apple has stuff that you can hook up to your TV that you can watch movies from iTunes. And the point of that is all of it is real time, meaning if it drops a packet and you're watching TV and you see a little glitch in the upper corner because the packet that showed the color for that glitch got dropped, so it just kind of scrambled it up there. Well, you're watching TV in real time. We don't, the packet got dropped. Boo-hoo, let's weep a little bit. But it's not that big a deal because, the scramble happened. I guess my point is that there's no purpose in backing everything up and going, whoa, stop. Boom, the whole screen freezes. And the server that's sending the video to you says, we need to send that packet that puts that little pixel in the upper right-hand corner that's the blue color. The packet comes out. You're sitting there watching the screen just frozen. And all of a sudden you see, bink, a tiny little 16th of an inch pixel in the upper right corner of your screen turns blue. We don't care about that because it's all happening in real time. So to stop everything while we wait for the packet that was lost makes no sense at all. It gets even worse if you think about voice over IP, speaking across the network. You can't even imagine that. So things that happen in real time will typically choose an unreliable transport because if you drop it, it's gone. I don't know if you've ever heard of, what is that? Deep Thoughts by Jack Handey. But there's one of them that just cracks me up every time I think about it. It's just Deep Thoughts. It's a Saturday Night Live thing. You're watching just this beautiful scenery, and Jack Handey came on and he said, if you're ever walking in a mountain and you drop your car keys in a stream of lava, just forget it, man. They're gone. That's the deep thought. So in the sense, if you're dropping packets, just forget it. It's gone. Now, the other half of the transport services, or this transport layer, is something known as port numbers. Now, we're going to get heavy into port numbers a little bit later, but the transport layer describes what's known as well-known services. And what port numbers allow you to do is designate exactly what service you're trying to access. Again, let's say we have a server over here and a client over here, and we want to, surf the web. Well, the web application, we'll put Internet Explorer, has to go to that server and grab the web page, but the server has to know that it's asking for the web page. Meaning this server might also, in addition to being a web server, it might be an email server and have a bunch of email for people. So it needs to know that this client is asking for a web page, and port numbers is how it knows that. It knows what application to send the request to, meaning the web server instead of the email server, because of this concept of port numbers. Like I mentioned, more on that later. So let's move down one more, the network layer. We will camp at the network layer for probably 3 or 4 nuggets later on in the series. But the network layer provides something known as logical addressing, meaning most people know this as the IP address. So when you assign an IP address to a computer or server, it's all happening at the network layer. This layer also finds the best path to a destination. So when you go to www.cisco.com, the computer has to go around the world through the internet to probably San Jose, which is where a lot of Cisco hosting happens, San Jose, California. And from wherever you're located in the world, all of the routers in between have to find the best path to get there. That's a function of the network layer. You move down to the data link layer, oh, right here, and now you have something known as physical addressing. Most people call this the MAC address. This is an address that's burned into a network card that when you buy a network card or a computer with a network card from the store, it's going to have an address that's physically burned into that device. Now that is used for communicating just on your local network, meaning it allows me to speak from my computer to the computer down the hall or to a server that's just a couple switch ports away. It's all local. It also ensures that the data is error-free. So as the communication passes down here, it's going to put a little check on there. So when it's received at the other side, it makes sure that nothing changed from the moment it was sent to the moment it gets there. Now I know right about now, it's probably where you're looking going, wow, this is all starting to just become one big blur of technology. Don't worry, on the next slide, I'm going to go through these in a real world example and show you how they're all used. Now the last layer that we have here is the physical layer. The physical layer is where we have physical access to the cable. And we move from all of these logical concepts down into electric signals. It converts all of these different features that we've chosen, reliable transport, certain IP addresses, certain MAC addresses, and generates electric signals that represents each one of those and sends them across the cable to the other sides. So most of the time when you're thinking of physical layer, or if there's a problem with the physical layer, you're usually thinking, oh, there's something wrong with the cable or the network card. It's something physically disabled in the network. Now that you've seen the OSI model layer by layer and function by function, let's take that theory and put it into a practical example in what I call OSI model in the real world. Now I have to warn you before we go through this example that this, I believe, will help demonstrate the OSI model much better than just knowing the definitions. It's kind of like if you're a doctor, seeing all the different equipment that you use, like a stethoscope and a shot needle and that sort of thing, and actually watching it in action. You really get two different perspectives. But I have to warn you that as we go through this, you will be seeing things we haven't talked about yet. Meaning, we may get down to the transport layer right here, and then we get into things called port numbers. And we haven't fully talked about port numbers yet, but we will talk about them. So if you see something that looks a little hazy, don't worry. We'll be fully covering that as we get into TCP/IP. So here's our story. We have a client over on the left-hand side that is using Internet Explorer to surf a website. We'll say they're going to www.cisco.com. So they go into their web browser and type in cisco.com. Now behind the scenes, that computer sends a message to a DNS server. DNS stands for Domain Name Service. And what that does is transform that friendly name that you and I recognize, Cisco.com, into Cisco's IP address. And again, we'll get more into that in just a moment. So we'll say that DNS server came back to that computer and said, well, Cisco's IP address, which is represented by that server over there, is 200.1.1.1. That's the IP that you want to access. Now us over here, we'll say that we are 10.1.1.5. That's our computer's IP address. So now the web browser, we typed in cisco.com, behind the scene knows that it needs to really go to 200.1.1.1. So the application layer says, send me a web page, because that's what Internet Explorer's request is. In HTML format or HTTP request, it says, please get Cisco's website. It packages that request into a generic format, HTTP. That's a well-known standard that we know and love and we use every day in our web browser. This passes it down to the session layer, and the session layer says, okay, there is a specific request for Cisco.com. I'm going to separate that, create its own session so that I don't get confused when I get all this other stuff coming back in. I mean, maybe this guy's listening to online radio and downloading from iTunes or something all at the same time. You don't want that computer to get confused with all the data coming in. It has to logically separate it. That's what the session layer does. It then passes it down to the transport layer. The biggest layer of all. And this is the one that I was saying. This is, I would say, the most important layer of the whole OSI model. Two choices are made here. First off, the choice of reliability. In our TCP/IP terms, well, we're choosing between reliable and unreliable. In TCP/IP terms, that's a decision between TCP and UDP. Now remember, these are some things that we haven't talked about fully yet. We will fully talk about them as we get into TCP/IP in the upcoming videos. So our web browser, Internet Explorer, is hard-coded by the people who made it to use TCP. So that says this will be a reliable connection. TCP is the reliable side. UDP is considered unreliable. Think of U as unreliable. Now, what does reliable mean? Well, it means that when I send that request to Cisco.com, the Cisco server is going to receive this down the road and get it, and is required by the TCP protocol to send back an acknowledgement saying, hey, I got your request. I received your request. I'm currently processing it. Hang on, let me give you that web page. So TCP is chosen. That's the first big decision. The second big decision is a hard coding of source and destination port numbers. Meaning, the transport layer partners with that session layer in assisting in keeping everything separate. We are using a web browser, and that web browser is sending a message over here to this web server. But what if that web server was also an email server? Or what if that web server, email server also was a why is a database server? There we go. I'm thinking, what other servers are there? It's a database server. So it does three functions. It's a web server, an email server, and a database server. We need to make sure that the message coming from Internet Explorer gets sent to the web server application, which is Apache in this case. That's my little flower or feather right there. I want to make sure that that message goes up into the web server software and doesn't get grabbed by the email server software and think I'm requesting some sort of email message or something like that. So in order to do that, my web browser, my operating system, hard codes a destination port number of 80. Now, we will be getting into all the well-known port numbers and what they do, but 80 happens to be the well-known port number for HTTP. So when I say 80, all of the services on the PC in the web server say, oh, well, that goes to the web server application. 80 essentially equals web. So that way, when this server over here receives the message from my computer, it's going to say, you're going to a destination port of 80. That will be sent to my Apache web server program. Just to expound on that a little bit, the email server inside of there, maybe it's running Microsoft Exchange. That email server responds to port 25. So all the other email servers of the world that send email to that server would be sending it to a destination port of 25. But we're not going to 25. We're going to port 80. Now that's the destination port number. That's how I make sure that it goes to the right destination service. But I also mentioned that the computer will assign a source port number. That source port number is going to distinguish that web browser application from everything else running on my computer. For example, I might have not only that web browser open, but maybe another web browser that's at the same time going to CNN.com to get some news. Well, the computer needs a way to know that when all the data is coming back in, the data from Cisco goes to this web browser and the data from CNN goes to the other web browser. So this web browser is assigned on the fly. They just kind of make one up. It's known as a dynamic source port number. We'll say 1098. So when it goes to the web server, it's going to say, hey, web server, I'm going to a destination port of 80. The server goes, great, I'll send you to my Apache web server program. But it will also say, I'm coming from a source of 1098. So when you send back to me, please be sure to use that as your destination port number. So when the web server, and this is down the road, says, I'm going to send you that web page, it's going to come from a source of 80. It's coming from the web server software. It's going to go to a destination of 1098. So that will allow my computer, when it receives it, to go, oh, you're going into that Internet Explorer window. You're not going somewhere else. Matter of fact, check this out. Here's a good way to demonstrate this. I'm going to, I didn't plan on doing this, so if it botches up, forgive me. I'm going to open a command prompt. And I'm going to create an FTP session. That's a file transfer session from here to Cisco.com. So I'm going to type in FTP, ftp.cisco.com. Enter. As I mentioned, I'm flying without a net here. Okay, good. So we connected. You can see that I'm sitting at this little user page right here for the ftp.cisco.com. I'm going to do it again. I'm going to open another command prompt window in this chaos and say I want to create another FTP session, FTP to ftp.cisco.com. Poof, I'm there. So I now have two FTP sessions. I'm going to open one more command window. I'm going to type in a command called netstat. That will show all of the open sessions coming from my computer to elsewhere right now. Now, my computer's doing plenty of things. I actually have connections over to a server called Win2003, so it's got some sessions going there. But what I want you to focus on are these. I have two sessions. Notice, check that. This is awesome. I love this. Protocol is TCP because FTP is also a reliable session. Local address and foreign address. This is me. This is where I'm going to. So locally, my IP address is 172.30.2.50, and I'm going to FTP-San Jose, and it's probably hiding the rest of it. It should be .cisco.com. Windows does that a lot of times to make it look prettier. FTP-San Jose.cisco.com is that full domain name, colon FTP. Now, whenever you see the colon, that's where the port number comes in. So I'm going to a destination of Cisco's FTP server on port, well, FTP. I kind of go, because Microsoft likes to be friendly, right? And they hide a lot of the nitty-gritty behind the scenes. FTP actually uses port 21. Microsoft said, well, we recognize port 21 as FTP, so we'll just put the name there for you. But it should say, it to be technically accurate and not pretty, it should say colon 21 to say that I'm going to, foreign address, destination, I'm going to the FTP services on Cisco's remote server. Now I'm coming from, this is the other piece I want to demonstrate, my local IP address, colon 49610 and 49609. Now, what is that 49609? We know the IP address is me, but those, the 49609 and 10, are the source port numbers. When ftp.cisco.com sends data back to me, it will be sending it to the destination port 49609. So when my computer gets it, it goes, oh, great. You're going over here to this window. And the stuff sent to 49610, you're going to go over to this window. I have the two separate windows open up. Now, do I know which window is really 09 and 10? No, I don't know. Without getting into the operating system nitty-gritty behind the scenes, it just makes it up. And if I add one more to the mix, we're on a roll. Why not? Let's do it. FTP, ftp.cisco.com. I've lost. There we go. I'll hit the up arrow and do a netstat one more time. Look at this. Right there is the next one. Notice the other two sessions have timed out. You can see them in a state of closed wait. They're just waiting to die. It's essentially where they're at. But look at what happened over here. My new FTP session I just created got assigned the port number 49611. It's kind of going in this incremental deal. So that's the idea behind the scenes, is at the transport layer, we're choosing the reliability and we're choosing the port numbers. I spend so much time there because that is going to be critical, especially when we get later on in the series and start looking at access control. We'll have the ability to block certain port numbers, which can deny certain services for the network. Now let's move down to the network layer, and I'll start clearing off some of my gibberish I've scribbled all over the place. Moving down to the network layer, we've had our web browser chose its port numbers. Now at the network layer, it will add in the source and destination IP address. Remember I said network layer on the previous slide is our logical address. The source and destination IP represents the original source and the final destination. Now, in my little story that I just did, my source IP address, well, in my demonstration I just did, was 172.30.2.50. The destination IP address, oh, what am I doing? Somebody scream at me. Wah! right up here in my story on the screen, I was 10.1.1.5. And I'm going to a destination of the Apache web server 200.1.1.1. Now, the news about the IP address is that from start to finish, that IP address does not change. Now, to every rule, there is exceptions, but I will say that as a statement for now. From the beginning to the end, my IP address will not change. So it will always be coming from this source going to that destination. I emphasize that because we're about to move down here to the data link layer where your physical address comes in. And for a long time, I was so confused. I was always wondering when I saw these two addresses, I'm thinking, why do you need two? Right? I mean, if you got the IP address, you know where you're coming from and where you're going. So why do you need a source and destination MAC address? You know, the address that's physically burned into your network card. Why do we even use that when we have the IP address on hand? Well, here's why. When we're going from end to end to end and we're trying to reach our destination, we have to have two addresses, one that defines locally where we're going and one that defines the big picture of where we're going. Now, I know that doesn't seem to make much sense. Let me show you on this scenario how it works. We'll say that this source MAC address of this computer, and by the way, you can find this out on any computer. Just go to a command prompt and type in ipconfig/all. Right there is one of the MAC addresses on my computer. If I scroll back up a little bit, because I have multiple network cards in this computer. I have a lot of network cards in this computer. You can see, I'm trying to find my network card that's given the 2.50. Right there. It's right up at the top. I missed it. The physical address, that's my MAC address. So we'll say that this computer up here has the physical MAC address 00A01511B9F2. MAC addresses are in hexadecimal, so A through F are valid characters as well. So that'll be my source MAC address without rewriting that. Now, what is the destination MAC address? Well, that's where we get into a big discussion that we're not fully going to get into here on how end-to-end network communication works. The idea is this computer right here with the IP address 10.1.1.5 realizes that this computer, this server, Cisco.com, is not on its own network, meaning it's not sitting here plugged into the same switch as himself. Now, how does he know that? Well, he looks at the IP address and he says, well, I am of the network, we'll say 10.1.1.5. You are of the network 201.1. If you were on my network, your IP address would start with 10.1.1 as well. Now, like I was saying, this is getting into a big discussion of IP addressing, which we're not fully going to get into here. The point in the big picture is this computer knows that that server is not on its network. So instead of sending the message directly to that server, it needs to send it to its default gateway. Now, the default gateway, we'll say that's somebody's home. The default gateway is probably just some little D-Link, Linksys, Netgear widget, little box. You know, just the router you go by from Best Buy or Circuit City or something like that, and you stick in your house that runs your internet connection. Now, that router might have the IP address 10.1.1.1 and whatever IP address is assigned by the internet service provider, you know, whether it's cable modem or DSL or whatever service provider, you'll have an IP address on this side that's your public IP address. Now, the problem is this. If I wanted to send a message to that server, but I have to go through this router to get there, how do I do that? I mean, how do I send a message to this router but say, oh, sorry, router, it's not for you. I'm just using you to get to the server. Because if I did this, if I were to say, well, it's coming from a source of 10.1.1.5 and going to a destination of 10.1.1.1, that would be this router. And the router would get it and go, oh, this is a message for me. Thanks, buddy. You know, and it would, you know, maybe send back some D-Link homepage or something like that because the router would think you're trying to talk to it. Here's why we need two addresses. The IP address, as I mentioned, from end to end does not change. So we know it always came from this source and it's always going to that destination. Now the MAC address from end to end will change all the time, meaning the source MAC address will be my computer. Who do you think the destination MAC address will be? The router. This guy right here. Maybe his MAC address is 00B941111, whatever my pen dictates, 2222. Well, that'll be the destination MAC address that we put in the packet right here. So when the router gets it, it receives it because the switch transfers MAC addresses. It looks at those MAC addresses, and the router gets it and goes, oh, great, I got a message. It's my MAC address. Then it looks up one layer at the IP address, and it says, oh, this isn't for me. That was a false alarm. I thought you were trying to talk to me, but I'm looking at that destination IP address, and that goes to Cisco.com. And by the way, that's what routers do, is they figure out how to get to those IP addresses. So off your message goes to the service provider, and they'll figure out how to get to Cisco.com. More on that as we look at end-to-end communication, but that is an overview of why we have to have two addresses in every single packet that's sent. Where are we? What are we doing? We're trying to get to Cisco's web page, right? HTTP request to the session layer. It separates it. To the transport layer, it chooses a reliable port-based connection. To the network layer, it says, this is my source, this is my destination. To the data link layer, it adds the MAC address, source and destination MAC address to allow the local network to get those messages. Finally, we're down to the physical layer, and out we go to the wire, received at the router, and then hop by hop by hop all around the world, you'll eventually get to Cisco.com, who receives the message on the physical layer, physical network card. It receives that message at their web server, looks at the MAC address and says, oh, you're trying to get to my MAC address. Looks at the IP address, says, oh, you're trying to get to my IP address. By the way, that's how the server knows it's a message for it and not somebody else. It then looks up at the transport layer and says, oh, you're using a reliable connection and you're trying to get to my web server application. So I'll send you up further. Understand the HTTP code, separate session. The Apache application gets it and says, got it. Let me send the acknowledgement, the ACK, because that was chosen as a reliable connection. And then I will begin sending packet by packet through the exact same process the other way, all of the information that will give you Cisco.com in your web browser. Isn't that amazing? It's just amazing to me that that happens so fast. I mean, you go to Cisco.com and poof, there's the web page in your browser. And behind the scenes, this process that I just explained happens probably 50 times at 50 different devices for all kinds of different packets that make that web page up. Insane. I dare you. Next time you're at a relative's house and they go to Google.com or something to find something, stop them and say, let me explain to you what just happened to put that Google logo on the screen. Actually, that would be a great test to see if you really know what the OSI model does layer by layer. Is try explaining that to somebody else. They say the way to really know if you know something is to teach it to somebody. So let me wrap up. I know we've gone a little bit long in this video, but hopefully that's okay because the OSI model is so key. We talked about this mythical OSI model. You will never talk about networking without hearing the OSI model mentioned at some point. We walked through the layers of the OSI model, layer by layer, looking at the specific functions, and more valuable in my mind was applying the OSI model to real life, watching those functions as it applies to network communication between two devices. I hope this has been informative for you, and I'd like to thank you for viewing.